Welcome to Calculus.
Our stress tolerance level has risen so high that nothing phases us.
On this episode, Stevenson will demonstrate
What about relative extrema or local extrema? So let's briefly address that now. So here's our lovely f of x function. You remember it very wisely. And again, all the little points it has. So what would you consider to be a relative, or what's also can be called a local maximum? And also, what do you think could be a local or relative minimum on the closed interval? Hopefully you look at points B, C, D, and E as local extrema. B and D would be considered local maxes, and C and E would be considered local minimums. Now, you can also call them relative. So the idea of relative and local imply the same thing, it's just a different word. So what makes a value a local or extreme value? So in your book, they have this definition. And so again, I want to kind of break it down for you a little bit and just kind of explain what it is, because it's important to know how to read the text. So again, C is some point in your function. Now, it says C is an interior point. So remember, interior just means between the endpoints. And f of C just represents the output of whatever C is, okay? So essentially the y coordinate. So you have an x coordinate, which is C, and the f of C is your y coordinate. Now, if all the other values, remember f of x represents all the other outputs, if all the other outputs are less than this particular output evaluated at C, then that means it is the largest value in that area, though. The biggest thing here, though, it's on the open interval, which means is you're not going to look at the endpoints around that particular C value. And the reverse is true. If all the other points, all the other outputs are greater than your particular output, then that means that particular output, f of C, is got to be the lowest point. But again, it's on the open interval, okay? Some things to also consider is that you can have local extrema at endpoints, but that would be if the domain is half open. In other words, on the interval, one side has a bracket and the other side has a parenthesis, okay? So again, some vocabulary. Local extrema is also called relative, so you'll hear me go back and forth between both of those words. They're interchangeable. The other thing that's super important to remember is that every single absolute extrema has a local. Is also considered a local extrema. Now, we talked about that last year, and if you have your notes, you'll actually find it. Absolute extrema automatically become also local or relative. However, a relative extrema can't automatically be an absolute. Okay, so it's a one-directional way of thinking. So how can we find these extreme values? Essentially, what we want to do is look at where the derivative either is 0 or doesn't exist. So if you can figure out where your derivative is 0 or the derivative doesn't exist, then it's a candidate for an extreme value. It doesn't guarantee it, but it's a candidate. So according to the theorem 2 here, what it's telling you is that your local maxes and mins at interior points will happen if the derivative exists there and the derivative equals 0. These locations that we look at to test for extrema are called critical points. You're going to hear that word for the rest of the year. Critical points. A point that's in the interior of the domain where the derivative either doesn't equal 0 or doesn't exist is called a critical point. Do not assume every critical point is an extrema, though. Okay? Extreme values will only occur at critical points and endpoints. Make sure you know that. And critical points are candidates for extreme values. Again, like I said, it doesn't mean they're automatically extreme values. It just says, hey, check here. So you have to test it to determine if it is in fact an extreme value or not. So there is a process. So what I did is I made this flow map to help illustrate the process of finding absolute extrema. The first thing you want to do is figure out what's the interval of your function. That's super important because you're going to find candidates or critical points that you're going to look at, but you may not have to test because they're outside of your interval. And that's super helpful. Step 2 is figure out what's the derivative of your function. So all those skills we've been doing, all that practice we've been doing with derivatives, all comes into play now. Step 3, figure out where is your derivative 0 and where does it not exist. That's where you're going to generate your critical points. Tip, don't assume you will have critical points in both of those categories. You may have them only in one and not the other. And also, it's highly possible you could end up with no critical points at all. Step 4, once you find your x values, what you're going to want to do, check them against your interval. So you could end up generating a critical point that doesn't even exist in your interval. And that's perfect, because then you just exclude it. Less to test. Step 5, once you figured out all your values, you're going to make a table and you're going to evaluate them, including the endpoints. So important. Don't forget the endpoints. Lastly, you're going to look at your table of values and you'll be able to quickly determine what is your absolute maximum or what is your absolute minimum.